One of the things that's most difficult about laboratory teaching is trying to get students to perform calculations when they're working in the laboratory. We have two things working against us. One is that they're busy doing things, and most students have an awful time trying to think in the abstract at the same time as they're mixing solutions and working with instruments and so on. The second problem is that students become awfully confused when they do quantitative work in the laboratory and apply even simple algebra to laboratory problems. One of the most difficult problems they encounter is when it's necessary to do a dilution to a known concentration. They know everything. They just need to calculate how much of this to add to that, and they will sit there with a blank stare. Part of the problem is that we don't define the objective in the first place. I'm going to describe two kinds of dilution problems and how to solve them, and they're both based on the same principle, both solutions. One is to take a stock solution of known volume, dilute it to a different concentration, a known final concentration. In that case, we don't know what the final volume is, and that's what we need to determine. In the second case, we want to take an unknown volume of our starting concentration, dilute it to a known final concentration and desired final volume. Both of them operate on the same principle. Now, first of all, if we define the objective, we're in good shape. Let's suppose we're going to do the first one. We want to take a known volume of stock solution and dilute it to some known final concentration. What do we know? What we know is, as a common frame of reference, that the amount of substance in our known volume of starting material, that is, the amount is the concentration times its volume. Let's let the initial concentration be C1 in moles per liter, and let the initial volume be V1 in liters. C1 times V1, moles per liter times liter, equals moles, equals the amount of substance that we have in that starting volume. If we know C1 and we know V1, we know the amount. Now let's take this volume, V1, and throw in a bunch of water. We'll say it's an aqueous solution. We'll just take this volume, let's say that this volume is 200 milliliters, and add a whole bunch of water to it. We know that it's going to dilute this concentration here, so C2 is going to be different. All right? Whatever C2 is, C2 times V2, the final volume, is the same because the amount of substance doesn't change. We're not throwing away any of the solute. Let's say it's sucrose that we're diluting. The concentration of sucrose times the volume of the solution tells us the amount of sucrose we have in moles. The concentration after we add some water, concentration, the new concentration times the new volume equals the same amount of sucrose. That doesn't change. So we have this relationship, C1V1 equals C2V2. What we have to do when we set up a problem is we have to decide what do we know, what are we trying to find out. And so if we're taking a known volume of stock solution of known concentration and we want a desired final concentration, we know the first C1, the initial concentration, we know V1, the initial volume, we know C2, what is going to be our final concentration, and all we need to determine is V2. I'll give you an example. What we have, let's see, for concentration number 1, let's take a look at this. I wrote up this nice example. I should use it. We have an initial volume of 500 milliliters here of a sucrose solution. And it is 325 millimolar. That's our concentration. So C1 equals 325, V1 equals 500 milliliters. Okay. Now what we want is our final concentration is 200 millimolar. So this, the desired final concentration, is 200 millimolar. All right, and we don't know what V2 is. We have an equation we can now set up. We can calculate V2 simply by doing the algebra. right? V2, the unknown, equals C1 times V1 divided by C2. In this case, we take 325 times 500 divided by our desired final concentration, 200 millimolar. The units will cancel out and give us units of volume. And not being a human calculator, I'm going to look up the result that I already determined, and that comes out, in fact, to 0.8125 liters. Okay. Now I've got graduated cylinders that are accurate to the nearest milliliter. I would use, for 0.8 liters, I would use a 1 liter cylinder, which is quite large. That's not going to be accurate to the nearest milliliter, maybe accurate to the nearest 5. Am I really worried about that? Not really. Not when we're talking about this kind of a dilution. We don't need that kind of accuracy. So what I'll do is simply use a final volume of 810 milliliters, and that will be just fine. That will put us well within 1% accuracy. So to recap, we knew the starting concentration of our stock solution. We knew the starting volume. We decided to start with 500 milliliters, so that's fine. And those two values give us the amount that we're starting with. We know what final concentration we want. Therefore, we had no problem in calculating the final volume that we want, and that is the final volume of the solution. If we're going to add water in order to get a final volume of 810 milliliters, 0.810 liters, we started with 500 milliliters. That means we have to add 310 milliliters to our starting solution, and we'll accomplish our dilution problem. Now, what I'm going to talk about next is a little more complicated, and it even throws off students worse, and that is how to take a starting solution and dilute it to a known concentration and a desired volume, both. That means we know C2 and V2, and we have to figure out what V1 is. This usually throws students off because they don't know how to set up the problem. What amazes me about this is that we live in a highly technical information age, and here I am writing on the wall with a piece of rock. Anyway, one of the problems that I guess difficulties that my students encounter, and one of the things that we commonly do in the lab, is to take a sample and dilute it to both a known volume and a desired final concentration. I ask my students to do this, for example, when they prepare protein samples to run on an electrophoretic gel. I'll use a typical protein concentration that we acquire as an example. Let's suppose that the student starts off with a protein sample of blood plasma. We want to run it on the gel and kind of look at what the proteins are in the blood plasma. In order to do that, we want to dilute to a particular concentration, in the ballpark that is, so we don't overload the gel or load too little. Let's suppose that our starting concentration is 11 milligrams per milliliter. Okay, that is C1. 11 milligrams per milliliter is the same as 11 grams per liter, by the way. Milligrams, milliliters are both 1,000th of the corresponding unit. Similarly, we could work with micrograms, microliters, and so on. As a matter of fact, what we want to do is take our initial concentration, take some volume of this sample, and dilute it so as to make 100 microliters. That will be V2. That's microliters, 1/1,000,000th of a liter. And a desired final concentration, C2, which is equal to 1 milligram per milliliter. Well, let's see what we have here. We have concentration units that match. 11 milligrams per milliliter, sorry, and 1 milligram per milliliter. Our final volume, desired volume, is in microliters. I'm not worried about matching up the volumes and using corresponding units because V1 is not calculated yet, and the calculation that we arrive at will be, in fact, in microliters. Now, where students get mixed up is in figuring out what they're calculating, what they're doing with this calculation, what they know and what they don't know. The objective is to find out what volume of this starting material, protein sample, we need to start with to dilute with buffer up to a final volume of 100 microliters. What is V1 going to be? Okay, we take C1 is 11 milligrams per milliliter, and C1 times V1 gives us our starting amount, 11 mg per mil, times V1, we don't know. Ooh, I got confused myself. Okay, we know that C1 times V1 equals C2 V2, and we don't know either quantity. We know both quantities, don't we? We know C2 is equal to 1 milligram per milliliter, and we know that V2 is equal to 100 microliters. Okay, this amount, 1 milligram per milliliter times 100 microliters, is exactly the same as this amount, 11 milligrams per milliliter, times this unknown volume. Because we're going to take this volume and add buffer to it that contains no protein to get our final solution in the volume V2. So again, we do the algebra. V1 equals, in this case, C2 V2 divided by C1. Or, to go ahead and do the arithmetic then, C2 V2 is 1 milligram per milliliter times 100 microliters, which is equal to 100. I won't add the units, it's a little complicated right now. Divided by C1, which is 11 milligrams per milliliter. Milligrams per milliliter cancels out, leaving us microliters. 100 divided by 11 is approximately 9. My pipetters don't measure with greater accuracy than 1 microliter anyway. This is just for a gel electrophoresis experiment, and all we need is a ballpark estimate. We could probably have gone with a simple 1 to 10 dilution, and that would have been fine. But 9 microliters is the answer. We could do this regardless of the starting concentration, regardless of the final concentration, final volume. The numbers themselves shouldn't confuse us at all. It's a matter of first, know your objective. What is it you want to find out? What starting volume should I use? We know everything else. Or, in the other case, what final volume do we need in the first case where we diluted a stock solution? And then we simply take the formula C1 V1 times C2 V2 and we do the algebra. One more time, I have had students come up to my office who recite this formula. They've had it before, they've used it before. What throws them off is they don't know the objective. They don't set up the problem in the first place and figure out what it is they're trying to accomplish. You do that, and I think you're going to eliminate a lot of confusion. Give them plenty of practice, because even my students who are pretty sharp have an awful time with this sort of thing. A convenient way of making dilutions when we don't really need accuracy and we need to make a succession of dilutions is to use serial dilutions. Now, we have to remember something about serial dilutions. It's not terribly accurate, but sometimes it's very convenient, because when we're doing, say, an assay, and we have no idea the starting concentration of our material, we need to find out at what point in terms of dilution we start to get in the range of the assay, a sensitivity of the assay. Another example is if we have a bacterial sample in broth, let's say. We want to plate out bacteria and get a certain amount of viable bacteria per unit volume. Well, bacteria can be extremely concentrated, and even when we dilute them as much as 60, 100, 1,000, 10,000-fold, they may not be diluted enough to give us separate colonies on a plate. So we do serial dilutions to rapidly dilute from high concentration to many orders of magnitude lower concentration. I'm going to demonstrate serial dilutions using the dye solution that I showed you a while back. I think it was in part 1, as a matter of fact. To begin, I'm going to dilute my dye in water. To begin, I took 6 small 50 milliliter Erlenmeyer flasks and to each one I added 40 milliliters of deionized water. I'm going to use a 10 milliliter graduated cylinder to make my measurements. Now I'll start with the concentrated dye, and I will need my glasses in order to see the units here. Error is cumulative, so we do want to be fairly precise with this one. Okay, that's close enough. And I'm going to add my dye to the first flask. There we go. That mixed pretty well. I'm going to make sure it's good and swirled up. And now this contains the concentrated dye right here. So what I want to do is give this a quick rinse. If I try to take my diluted solution and pour it in here on top of the concentrate, I'm going to add some error that I don't need. That quick rinse is enough. See, there's some in there, okay? Now what I'll do is take my first 1 to 5 dilution, and I'll put it in here, 10 milliliters out, and I will transfer 10 milliliters of that dilution to the second flask. There we go. Let's swirl it up. You might notice a difference in color. So we're accomplishing the dilution. This is 5-fold diluted. This is another 5-fold, 5 times time, 25-fold dilution. Okay? I'm going to do this one more time. Let's rinse our cylinder off a little bit. And now I'm going to make sure our second dilution is quite rinsed. I'm going to go ahead and, or mixed rather, and let's carefully fill up our, there we go, cylinder, and we'll add it to the third flask. Notice the color is even lighter. In fact, it's even changing in quality. There's our 3 colors. We now have a 1 to 5 times 25, a 1 to 125 dilution. We're getting down there very fast. This one would be 1 to 625. This one would be 1 to about 3,000 or so, and this thing would be more than a 15,000-fold dilution. Oh, a couple more of these and would be very, very diluted, and the color would start to disappear. If you want to go down faster in orders of magnitude, make your dilutions 1 to 10 instead of 1 to 5. You can make them 1 to 20 if you want to, whatever you'd like to. This is very convenient. Just keep in mind that errors are accumulative. If we're making a 10% error each time we do these mixes, we could be way, way off by an order of magnitude by the time we get down.